Most of us look up at the night sky with a quiet assumption. The stars and galaxies above us feel like they belong to the present moment, hanging there exactly as they are right now. But the truth is stranger and far more beautiful. Every point of the light you see in the sky is delayed, some by years, some by millions, and some by billions. The James Webb Space Telescope has begun revealing just how powerful that delay really is, because when we look far enough into space, we are no longer seeing the universe as it is. We are watching it grow up. If you enjoy journeys like this, quiet explorations of the real universe, consider subscribing. And now, let's begin with something familiar. Step outside on a clear night and look up. Even in a city, a few stars push through the glow of streetlights. In darker places, the sky fills with thousands of them, scattered like frost across black glass. It feels immediate, present, as though those stars are simply there, shining down in the same moment we are looking at them. But light does not move instantly. It travels incredibly fast, faster than anything else in nature, but it still takes time to cross distance. Light from the moon reaches Earth in just over 1 second. Light from the sun takes about 8 minutes. When sunlight warms your face, what you're feeling actually began its journey before you poured your morning coffee. That small delay is easy to accept. 8 minutes does not feel dramatic. But space is not built on small distances. The nearest star beyond the sun is more than 4 light-years away. When you see it, you're seeing light that began travelling toward Earth 4 years ago, somewhere in the universe. That star exists as it is today, but the version you see belongs to the past. And the farther away you look, the further back that past becomes. A star 1,000 light-years away appears as it was when people on Earth were building medieval cathedrals. A galaxy 10 million light-years away shows us light that began its journey before the earliest human ancestors walked upright. This is not a trick of perception. It is a fundamental feature of the universe. Distance is time. The night sky is not a snapshot of the present. It is a layered archive, a collection of messages sent long ago, arriving tonight. Once you understand that idea, something extraordinary begins to happen. The universe becomes a timeline. Imagine standing in a museum where every object comes from a different century. A Roman coin beside a medieval sword beside a 19th century telescope. By walking from one display case to another, you are quietly walking through history. Now imagine that the sky works the same way. Nearby stars show us the universe almost as it is now. Distant galaxies show us the universe millions or billions of years earlier. The farther we look, the deeper into cosmic history we see. Astronomy, in a sense, is archaeology done with light. For decades, telescopes have been reading that history. The Hubble Space Telescope showed us galaxies billions of light-years away, revealing that the universe was once younger, denser, and filled with more frequent star formation. But even Hubble had limits. The earliest galaxies are incredibly distant, and something subtle happens to their light as it travels across the expanding universe. Space itself stretches. Galaxies move apart not because they are flying through space like shrapnel from an explosion, but because space between them is expanding. As light crosses that expanding distance, its wavelength stretches too. The colour slowly shifts. Light that began as ultraviolet becomes visible. Light that began as visible red becomes infrared. This effect is called redshift. It is similar to the change in pitch you hear when a siren passes by. The sound waves stretch as the source moves away, lowering the tone. Light behaves in a comparable way across cosmic distances. For the most distant galaxies, the ones formed only a few 100 million years after the Big Bang, the stretching is enormous. Their original light has shifted so far that it now arrives at Earth almost entirely in infrared wavelengths, which means that if you want to see the earliest chapters of the universe, you need a telescope designed to see infrared light. That is exactly what the James Webb Space Telescope was built to do. Webb does not orbit Earth like Hubble. Instead, it sits about 1.5 million kilometers away, at a quiet gravitational balance point called L2. From there, it unfolds its enormous golden mirror and spreads a tennis court-sized sunshield that blocks heat from the sun, Earth, and Moon. This cooling is essential. Infrared light is closely related to heat, and if the telescope itself were warm, its own temperature would drown out the faint signals arriving from deep space. Webb must remain extraordinarily cold so it can detect the faint glow of galaxies that formed when the universe was still in its infancy. With that sensitivity, Webb can see things previous telescopes simply could not. Galaxies whose light has been travelling for more than 13 billion years. Objects that existed when the universe was less than 5% of its current age. To appreciate what that means, compress the entire 13.8 billion year history of the universe into a single calendar year. The Big Bang happens at midnight on January 1st. The first stars ignite sometime in mid-January. For most of the cosmic year, galaxies are slowly forming, merging, growing larger. Our own galaxy, the Milky Way, gradually takes shape through countless interactions. But Earth does not appear until early September. Multicellular life arrives in December. Dinosaurs walk the planet around December 25th. Human civilization appears in the final seconds before midnight on December 31st. Now imagine a telescope powerful enough to look back to mid-January of that cosmic calendar. That is roughly what Webb is doing. When its mirrors gather light from the most distant galaxies yet observed, we are seeing structures that existed only a few 100 million years after the universe began expanding. These are not just ancient objects. They are early chapters of cosmic history itself. For a long time, astronomers expected those early galaxies to be small and primitive. The universe had not yet had much time to build complexity. Stars would have been forming for the first time. Heavy elements would have been rare. Galaxies would be faint, irregular clouds slowly assembling themselves. That expectation came from decades of theoretical models. And to some extent, the models are right. But Webb has begun revealing something unexpected. Some of those early galaxies look surprisingly mature, more structured, more massive, more active. In some cases, galaxies that appear only a few 100 million years after the Big Bang already contain enormous numbers of stars. They show signs of complex chemical enrichment. Some even appear to host rapidly growing black holes at their centers. In other words, the early universe may have been building galaxies faster than we once imagined. To be clear, this does not mean our understanding of cosmology is collapsing. Observations always need careful interpretation. Astronomers are still analyzing the data, refining distance measurements, and improving models of early star formation. But the message emerging from Webb is unmistakable. The earliest universe was not a quiet place. It was a time of astonishing activity. Stars igniting in enormous clusters, gas clouds collapsing under gravity, galaxies merging and reshaping each other, black holes feeding and growing. And every one of those events left traces in the light now reaching our telescopes. When Webb takes a deep field image, staring at a tiny patch of sky for hours or days, it reveals thousands of galaxies in a single frame. Some relatively nearby, some billions of light years away, some whose light began travelling toward Earth before our planet even existed. Each one is a different moment in the universe's past. Seen together, they form something remarkable. Not just a map of space, but a living timeline of cosmic evolution. And as Webb continues to peer deeper into that timeline, the story only becomes richer, because galaxies themselves are not isolated islands. They are part of a much larger structure that began forming almost immediately after the universe itself came into existence. If you could step far enough away from the Milky Way and look at the universe on its largest scales, it would not appear random at all. Galaxies are not scattered evenly through space like grains of sand tossed across a floor. Instead, they trace enormous patterns, vast threads stretching hundreds of millions of light years, intersecting in dense knots where thousands of galaxies gather together. Astronomers call this structure the cosmic web. Imagine an immense three-dimensional network of glowing rivers. Along those rivers, galaxies form, feed, and evolve. Between them lie enormous voids, regions so empty that a traveller could cross tens of millions of light years without encountering a major galaxy at all. This architecture began forming very early in cosmic history. Not long after the Big Bang, the universe was almost perfectly smooth, but almost is the key word. Tiny fluctuations in density, differences so small they were only 1 part in 100,000, were already present in the hot plasma filling the newborn cosmos. Those slight irregularities became seeds. Gravity does not need large imbalances to begin its work. Even the smallest concentration of the matter pulls in surrounding material, growing gradually stronger as it accumulates more mass. Over millions and then billions of years, those early fluctuations amplified themselves. Denser regions gathered gas and dark matter. Less dense regions slowly emptied. What began as faint ripples eventually became the enormous filaments and clusters we see today. The cosmic web is the skeleton of the universe, and galaxies are its luminous organs. But here is where the James Webb Space Telescope enters the story in a completely new way. Because Webb is not just showing us where galaxies are located, it is allowing us to see how those galaxies change as the universe ages. To understand why this matters, return to that simple but powerful idea: distance equals time. In a single deep image captured by Webb, we may see galaxies that are 1 billion light-years away, 5 billion light-years away, and 12 or even 13 billion light-years away. Those are not just different distances. They are different eras. The closer galaxies appear as they were relatively recently in cosmic history. The farthest galaxies appear when the universe was only a few 100 million years old. So when astronomers analyze a Webb image, they are not looking at a single moment frozen in space. They are comparing multiple ages of the universe at once. Imagine walking through a forest where each tree represents a different century of growth. Some are ancient and towering, others are young saplings, some have recently merged with neighbouring trunks, forming thicker structures. By studying them together, you begin to see patterns, how trees grow, how forests change over time, how individual lives connect to the wider ecosystem. Galaxies behave in a surprisingly similar way. They are not static objects. They grow, they merge, they transform, and Webb's extraordinary sensitivity allows us to examine these processes across a vast range of cosmic time. For example, one of the simplest ways a galaxy grows is through star formation. Inside galaxies are enormous clouds of hydrogen gas, cold, dark regions where gravity slowly gathers matter into denser pockets. When enough gas accumulates in one region, the pressure and temperature rise until nuclear fusion ignites. A star is born. This process can occur quietly, producing a handful of stars each year, or explosively, creating hundreds or even thousands of new stars in intense bursts known as starbursts. Webb's infrared instruments are particularly good at detecting these regions because infrared light can pass through dust clouds that block visible wavelengths. In effect, Webb can peer into stellar nurseries that were previously hidden from view, and when astronomers observe distant galaxies with Webb, they are seeing star formation happening billions of years in the past. What emerges from those observations is a powerful trend. The early universe was forming stars at a remarkable rate. In fact, if you travelled back roughly 10 billion years, the average galaxy in the universe was producing new stars several times faster than galaxies do today. Our own Milky Way currently forms about 1 or 2 new stars each year. That may sound impressive, but in earlier cosmic eras many galaxies were producing dozens, sometimes hundreds, annually. The universe had more raw fuel then. Hydrogen gas was abundant, and galaxies were colliding and merging far more frequently. Those mergers compressed gas clouds, triggering waves of star formation that lit up entire galaxies. It was a time of cosmic adolescence. Fast growth, rapid change. And Webb is now giving us an unusually clear view of those formative periods. One of the most fascinating tools astronomers use with Webb is spectroscopy. At first glance, a galaxy might appear as nothing more than a faint smudge of light. But when that light is spread into its component wavelengths, much like sunlight passing through a prism, it reveals a detailed fingerprint. Certain wavelengths are absorbed or emitted by specific elements. Hydrogen produces one set of lines, oxygen another, carbon, nitrogen, iron, neon, each leaves its own signature in the spectrum. By studying those patterns, astronomers can determine the chemical composition of galaxies billions of light-years away. And those chemical clues tell an important story. The universe did not begin with heavy elements. Immediately after the Big Bang, the cosmos was dominated by hydrogen and helium, with only tiny traces of lithium. All of the heavier elements, carbon, oxygen, silicon, iron, gold, were forged later inside stars. Stars act like enormous furnaces. Deep within their cores, nuclear fusion combines lighter atoms into heavier ones. When massive stars reach the ends of their lives, they explode as supernovae, scattering those newly created elements into surrounding space. Over time, this enriches galaxies. Each generation of stars inherits material from earlier generations. Gas clouds become increasingly seasoned with heavy elements, allowing new stars to form with more complex chemistry. This gradual enrichment is one of the clearest markers of cosmic evolution. Young galaxies in the early universe should contain fewer heavy elements. Older galaxies, having hosted many cycles of star birth and death, should contain far more. And Webb is now measuring those chemical fingerprints across enormous distances. Some early galaxies show exactly what we expect: extremely low metallicity, meaning they contain very few heavy elements. These systems likely resemble the conditions under which the very first stars formed. But other galaxies, again, surprisingly early in cosmic history, already appear chemically enriched. That suggests that star formation may have begun earlier and progressed faster than older models predicted. In other words, the universe may have started building complexity very quickly after its initial expansion. Another piece of the puzzle involves black holes. At the center of nearly every large galaxy lies a supermassive black hole. The one at the center of our Milky Way contains about 4 million times the mass of the Sun. Some in distant galaxies are far larger, billions of solar masses. For decades, astronomers have noticed something curious about these giants. Their growth appears closely connected to the growth of their host galaxies. When galaxies form stars rapidly, their central black holes often grow quickly as well, feeding on gas and dust spiraling inward. When star formation slows, black hole growth tends to slow too. It is as though the galaxy and its black hole evolve together. But this raises an obvious question. How did such enormous black holes form so early in the universe? Webb is beginning to shed light on that mystery too. Some distant galaxies observed by Webb appear to host actively feeding black holes less than 1 billion years after the Big Bang. That leaves only a short window of cosmic time for them to grow from whatever seeds formed in the universe's earliest epochs. Astronomers are still working through the possibilities. Perhaps the first black hole seeds were already quite massive. Perhaps early galaxies channeled gas into their centers far more efficiently. Or perhaps the universe simply allowed black holes to grow under conditions that were more favorable than we previously realized. What matters for our story is that Webb is giving us direct observational access to those early systems. Instead of inferring cosmic evolution only through models and simulations, we're beginning to watch its stages unfold across the sky. Each distant galaxy is a page from an earlier chapter. Each spectrum reveals the chemical progress of stellar generations. Each black hole hints at the rapid construction of structure in the young universe. When you look at a deep Webb image, you are not just seeing distant lights. You are looking at a cross-section of time itself. Galaxies in childhood, galaxies in adolescence, galaxies approaching maturity. And as astronomers continue to analyze those images, one of the most profound realizations is slowly settling in. The universe has always been evolving, but for the first time in human history, we are beginning to see that evolution directly written across the sky. The idea that we can watch cosmic evolution unfold does not mean the universe is changing quickly in front of our eyes. Human lifetimes are far too short for that. Galaxies do not visibly grow between one evening and the next. Stars do not ignite or explode on a schedule we can easily observe across billions of light years. Yet the sky contains something almost as powerful, a natural record. When Webb stares into a small region of darkness and reveals thousands of galaxies, those galaxies are not all the same age. Some are relatively nearby, their light beginning its journey only a few 100 million years ago. Others are so distant that their light began travelling toward Earth when the universe was still extremely young. Placed together in a single image, they form something that looks almost like a geological cross-section. If you have ever seen a canyon wall where layers of rock reveal different eras of Earth's past, the comparison is surprisingly accurate. The deeper layers belong to earlier times. Higher layers represent more recent history. The observable universe works in a similar way, except the layers are made of distance. The deeper you look into space, the earlier the cosmic era you encounter. And the James Webb Space Telescope has extended that depth farther than any instrument before it. To appreciate just how far, imagine sending a message into space today at the speed of a light. If it travelled for 13 billion years before reaching its destination, that distance is roughly where some of Webb's observed galaxies lie. Their light has been travelling toward us for almost the entire history of the universe, and yet the signal is still detectable. That alone is astonishing, but the deeper significance comes from what those signals reveal. Because the earliest galaxies do not just appear fainter, they often appear fundamentally different. Astronomers expected young galaxies to be small, chaotic collections of gas and newborn stars. The universe was still assembling itself, after all. Gravity needed time to pull matter together into the grand spiral and elliptical structures we see around us today. But in Webb's observations, some of those early systems already display signs of organization. They are not merely shapeless clouds. They are structured galaxies. In a few cases, they even resemble small disk-like systems that hint at early rotation, suggesting that gravitational organization may have occurred more rapidly than many models predicted. Again, interpretation takes time. Astronomers are careful with these conclusions. Distances must be confirmed through precise measurements of redshift, and galaxy shapes can sometimes be misleading when seen at enormous distances. Still, the trend is difficult to ignore. The young universe appears surprisingly capable of building large structures very quickly. One reason may lie in the extraordinary density of matter during those early eras. Today, galaxies are separated by immense distances. Collisions still happen, but they are relatively rare events on human timescales. The Milky Way, for instance, is expected to merge with the neighbouring Andromeda galaxy in about 4 billion years, a slow gravitational dance that will reshape both galaxies. But billions of years ago, the universe was smaller. Galaxies were closer together. Interactions were far more common. Think of storm systems in a crowded atmosphere. When clouds form near one another, they inevitably collide, merge, and reorganize. The same principle applies to galaxies, except the process unfolds across millions or hundreds of millions of years. Two galaxies approach. Their gravitational fields begin to distort one another. Streams of stars stretch outward like luminous tides. Gas clouds collide and compress, triggering intense bursts of star formation. Eventually, the two systems merge into a single, larger galaxy. This process, galactic merging, is one of the fundamental engines of cosmic evolution. Webb's observations show that it was already happening extremely early in the universe's history. Some distant galaxies display elongated shapes and tidal features that suggest interactions with neighbouring systems. Others appear unusually massive for their age, hinting that they may already be the products of earlier mergers. It is as though we are looking at a cosmic city during its earliest construction boom. Buildings rising quickly, neighbourhoods forming, roadways connecting distant districts. The universe in those early times was not quiet. It was industrious. But there is another transformation happening alongside these structural changes, one that is even more important for understanding the origins of complexity. Chemical evolution. When the first stars formed, they were likely very different from most stars we see today. Astronomers refer to them as population 3 stars, the earliest generation of stellar objects formed from primordial hydrogen and helium. Without heavier elements to help cool gas clouds, these early stars may have grown extremely massive, sometimes hundreds of times the mass of our Sun. Such giants burn their fuel rapidly and live short lives, sometimes only a few million years. When they die, they explode. These explosions scatter newly forged elements into surrounding space: carbon, oxygen, silicon, iron, the raw materials that later become planets, oceans, and even living organisms. In this sense, stars are not only sources of light, they are factories of chemistry. The earlier stars began the process of enriching the universe with heavier elements. Later generations inherited that enriched material, forming stars with increasingly complex compositions. The difference is measurable. Astronomers refer to the abundance of heavy elements in a star or galaxy as its metallicity. Systems with very low metallicity contain mostly primordial hydrogen and helium. Systems with higher metallicity have been shaped by many cycles of stellar birth and death. Webb's spectroscopic instruments allow astronomers to measure this property across cosmic time, and what they are seeing reveals the chemical maturation of the universe. Some galaxies observed less than 1 billion years after the Big Bang already show traces of elements like oxygen and carbon, clear signs that earlier generations of stars must have lived and died before them. This implies that star formation began very early, perhaps earlier than we once believed. In the deepest Webb observations, astronomers are beginning to glimpse galaxies that existed when the universe was only 300 or 400 million years old. These objects sit near the boundary of what current telescopes can detect. Beyond them lies a period known as the cosmic dark ages. Before the first stars formed, the universe was filled with neutral hydrogen gas that absorbed much of the light passing through it. The cosmos was not completely dark, but it lacked luminous objects capable of lighting the vast expanses of space. Eventually the first stars ignited. Their intense radiation began to ionize surrounding hydrogen, stripping electrons from atoms and making the universe more transparent to light. This transformation is called cosmic reionization. It was one of the most important transitions in the history of the universe. Without it, light from distant galaxies would remain trapped in opaque clouds of hydrogen. But the exact timing and duration of reionization have been difficult to determine. Webb is now providing new clues. By identifying galaxies from extremely early epochs and measuring their brightness, astronomers can estimate how much ultraviolet radiation those young galaxies produced. That radiation likely played a major role in gradually ionizing the surrounding hydrogen. The emerging picture suggests that reionization may have been driven by numerous small galaxies forming stars at extraordinary rates. Individually they were faint. Together they transform the universe. Think of a vast landscape at dawn. At first the horizon glows faintly as the earliest light appears. Then countless sources begin to illuminate the terrain: villages, cities, windows, fires. Slowly the darkness recedes until the entire landscape is visible. Cosmic reionization may have unfolded in a similar way. The first galaxies acted like distant lanterns, gradually lighting the universe. Webb is now detecting many of those lanterns. Each new observation adds detail to the picture. Each spectrum reveals another fragment of the early chemical story. Each galaxy at extreme redshift becomes a marker of how quickly the universe moved from simplicity to complexity. And perhaps the most extraordinary realization is this: all of those distant lights represent ancestors of the structures we see around us today. The Milky Way, the Andromeda Galaxy, the clusters and filaments stretching across hundreds of millions of light years. Everything we observe in the present grew out of those early phases of cosmic evolution. When Webb captures light from a galaxy that existed 13 billion years ago, we are not simply observing something distant. We are witnessing the childhood of the universe itself. And as the telescope continues to gather data, astronomers are beginning to notice that this childhood may have been far more energetic, far more creative than we once imagined. Which leads to an even deeper question. If the early universe was capable of building galaxies, stars, and black holes so quickly, what underlying structure allowed that rapid transformation to happen at all? To answer that, we have to look beyond the galaxies themselves and into the invisible framework that shaped their growth from the very beginning. The visible universe, the stars, the glowing gas, the galaxies themselves, only tells part of the story. Beneath that luminous surface lies something we cannot see directly, yet whose influence shapes almost every large structure in the cosmos. Dark matter. It does not shine. It does not emit light or absorb it in any obvious way. If you placed a cloud of dark matter next to a star, the star would illuminate nothing. Your eyes would see empty space. And yet the universe behaves as though vast amounts of invisible mass are present. Galaxies rotate faster than they should if only their visible stars were providing gravity. Clusters of galaxies bend the paths of background light more strongly than their visible matter can explain. Entire structures of galaxies stretch across space in patterns that require far more mass than we can account for with ordinary atoms. The simplest explanation, supported by many independent observations, is that most of the matter in the universe is dark. Not dark as in hidden by dust. Dark as in fundamentally invisible. And this invisible matter played a crucial role in the earliest chapters of cosmic evolution. To see why, imagine the universe shortly after the Big Bang. Everything was hot, dense, and filled with particles moving in every direction. Ordinary matter, hydrogen and helium, was tightly coupled to radiation. Light scattered constantly off charged particles, keeping matter stirred like foam in boiling water. Gravity was already present, but it struggled to gather ordinary matter into dense structures because radiation pressure kept pushing things apart. Dark matter, however, behaved differently. It did not interact with light. Without that constant radiation pressure, dark matter could begin clumping earlier, forming faint gravitational wells scattered throughout space. Think of it like invisible valleys forming beneath a shallow ocean. Ordinary matter, the gas that would eventually become stars and galaxies, drifted into those valleys over time. As the universe expanded and cooled, gas could settle into the gravitational structures dark matter had already begun shaping. Those valleys became the first seeds of galaxies. The cosmic web itself, the enormous network of filaments stretching across hundreds of millions of light-years, likely formed because dark matter gathered into threads and nodes under gravity's influence. Galaxies grew inside those structures like glowing embers within a vast invisible scaffold. Webb cannot see dark matter directly, but it can observe the luminous matter that traces its shape. When astronomers map the positions of distant galaxies, they find that those galaxies often align along enormous filaments, exactly where dark matter simulations predicted mass should accumulate. In some regions, the density becomes so high that clusters form, massive gatherings containing thousands of galaxies bound together by gravity. Elsewhere, enormous voids open up where matter is scarce. Seen on the larger scales, the universe resembles foam or sponge-like patterns, with bright structures outlining enormous empty regions. This is the architecture of cosmic evolution, and Webb is now revealing pieces of that architecture at earlier times than ever before. When the telescope detects distant galaxies only a few 100 million years after the Big Bang, it is effectively showing us where the earlier structures began to light up within that dark matter framework. Some of those galaxies appear isolated. Others appear close together, suggesting that small groups and clusters were already forming. The implication is remarkable. The cosmic web, the vast network shaping the universe today, may have begun organizing itself astonishingly early. To appreciate the scale of these structures, imagine shrinking the entire Milky Way galaxy to the size of a coin. At that scale, the distance to the nearest comparable galaxy would be several meters away. Entire clusters of galaxies would span kilometers. The filaments connecting clusters would stretch for hundreds of kilometers. Now imagine trying to map that enormous structure while looking backward in time across billions of years. That is essentially what astronomers are doing with telescopes like Webb. And every new observation adds another data point to the timeline. Some galaxies appear compact and irregular, their shapes still turbulent from recent formation. Others show smoother distributions of stars, hinting at more settled structures. This diversity is important. It suggests that galaxies evolve along multiple pathways. Some grow gradually through steady star formation, slowly converting gas into stars over billions of years. Others grow through mergers, combining with neighbors to form larger systems. Still others may experience powerful feedback from their central black holes, where enormous energy output pushes gas outward and temporarily halts star formation. All of these processes leave fingerprints. The colors of galaxies reveal the ages of their stars. Blue light often indicates recent star formation, while redder light suggests older stellar populations. Infrared observations, Webb's specialty, allow astronomers to measure the glow of warm dust heated by young stars. Together, these signals tell us how active a galaxy is and how quickly it's evolving. In many of Webb's early observations, astronomers noticed that young galaxies in the distant universe often appear extremely compact. Their stars are crowded into regions much smaller than typical galaxies today. Imagine compressing the entire stellar population of the Milky Way into a volume only a fraction of its current size. Such densities imply intense gravitational interactions between stars, gas clouds, and central black holes. They also hint that early galaxies may have grown outward over time, gradually expanding as mergers and stellar feedback redistributed matter. In other words, galaxies did not simply appear fully formed. They built themselves piece by piece, and the earliest pieces are now coming into view. But perhaps the most fascinating element of this story lies in the connection between cosmic evolution and something far more personal. The elements that make up our world. The oxygen you breathe, the carbon in every living cell, the calcium in your bones. None of these existed in the universe immediately after the Big Bang. They were created later inside stars. And because Webb can detect galaxies from extremely early cosmic eras, it allows astronomers to trace how quickly those elements began spreading through the cosmos. In some distant galaxies, Webb has detected signatures of oxygen and other heavy elements appearing surprisingly early. This means that multiple generations of stars must have already formed, lived, and exploded by the time that galaxies' light began its journey toward Earth. Those early stellar cycles began enriching interstellar gas long before our solar system existed, long before Earth formed, long before life appeared. The atoms that now circulate through living organisms were forged in stars that burned billions of years before our planet came into being. Seen from this perspective, cosmic evolution is not an abstract scientific idea. It is a chain of events leading directly to us. Each generation of stars inherits the chemical legacy of those that came before. Galaxies gradually accumulate heavier elements as stellar processes unfold. Planetary systems eventually form around young stars enriched by ancient supernova debris. Over time, complexity increases. Hydrogen becomes helium. Helium becomes carbon and oxygen. Dust grains form in stellar outflows. Planets assemble in swirling disks of gas and rock. On at least one small world orbiting an ordinary star in a quiet spiral galaxy, chemistry eventually became biology. That entire sequence depends on cosmic evolution unfolding across billions of years. And when Webb observes galaxies in the distant past, we're effectively watching the earlier stages of that chain reaction. We are seeing the universe building the raw materials of future worlds. But something else emerges from these observations too. A subtle sense that our place in cosmic time may be unusually fortunate. Because only now, after billions of years of star formation, galaxy assembly, and chemical enrichment, does the universe contain both the complexity necessary for life and the technological capacity for a species to observe its own origins. The ancient light reaching Webb's mirrors tonight began its journey long before Earth existed. Yet here we are, able to intercept it, to decode it, to understand that those faint infrared signals represent galaxies in the act of becoming, the universe evolving in plain sight. And as Webb continues its work, the story is becoming clearer, deeper, and in some cases more surprising than we expected, because some of the earliest galaxies now appearing in its observations seem to challenge long-standing assumptions about just how quickly cosmic structure could form. For many years, astronomers had a fairly clear expectation of what the earliest galaxies should look like. The universe, after all, had only just begun forming stars. Gravity needed time to gather gas into dense regions. Black holes had barely started to grow. The ingredients for complexity were still being assembled. So the first galaxies were expected to be small, dim, messy. They would contain relatively few stars, most of them young. Their shapes would be irregular, like scattered clouds rather than organized systems. And because the universe had not yet produced many heavy elements, those galaxies would be chemically primitive. That picture made sense. It matched the gradual, step-by-step process predicted by many cosmological models. Then Webb started looking, and almost immediately, astronomers began noticing objects that did not fit so neatly into those expectations. Some of the earliest galaxies detected by Webb appear surprisingly bright. Brightness in a galaxy usually means large numbers of stars, because each star contributes light to the total glow we observe. If a galaxy is very luminous, it likely contains a great deal of stellar mass. But here is the puzzle. Several galaxies observed less than 1 billion years after the Big Bang seemed to contain more stars than expected for such an early time. Not impossibly many, but enough to raise eyebrows. Imagine walking into a city that supposedly began construction only a year ago, yet already contains clusters of tall buildings and busy districts. The existence of those buildings would not violate physics, but it would force you to reconsider how quickly construction began and how efficient the builders were. That is roughly the situation astronomers now face with some Webb observations. The early universe may have been extremely efficient at forming stars. Part of this may come down to the availability of raw material. Hydrogen gas filled the young universe in enormous quantities. Galaxies could draw from this reservoir and convert it into stars at remarkable rates. Collisions between galaxies also happened more often, compressing gas clouds and triggering intense bursts of star formation. But even taking those factors into account, some of the observed galaxies still seem impressively mature for their age. Their structures look more organized than expected. Their masses appear larger. In a few cases, the systems look as though they have already undergone multiple stages of growth. Naturally, astronomers approach such findings cautiously. Distance measurements must be verified carefully, because redshift can sometimes be misinterpreted if unusual physical conditions affect a galaxy's spectrum. Early brightness estimates may also change as more precise observations are collected. Science rarely moves forward through instant conclusions. Instead, it refines its understanding step by step. Still, the pattern emerging from Webb's early surveys is intriguing enough that many researchers are now revisiting their models of early galaxy formation. Perhaps star formation began earlier than we thought. Perhaps the first gas clouds collapsed more rapidly. Perhaps early galaxies were able to gather matter more efficiently through the dark matter framework surrounding them. Each of these possibilities is now being explored, and the process itself is a perfect example of how science evolves. Observations lead, theories follow. When new data arrives, models adjust. This quiet conversation between telescope and theory is how our picture of the universe becomes sharper over time. But Webb's discoveries are not only challenging assumptions about galaxy size and brightness, they're also providing new insight into something even more dramatic: the growth of black holes in the early universe. At the center of many galaxies lies a supermassive black hole, often millions or billions of times heavier than the Sun. These objects are surrounded by swirling disks of gas and dust. As matter falls inward, it heats up and releases enormous amounts of energy. In particularly active galaxies, this process can create quasars, some of the brightest objects in the universe. Quasars were discovered decades ago, and even early observations revealed something puzzling. Some quasars appear extremely distant, meaning their light began traveling toward Earth when the universe was still very young. Yet their black holes were already enormous. Growing a black hole to billions of solar masses normally requires long periods of steady feeding. Gas must spiral inward over millions of years, adding mass gradually to the central object. So how did some black holes become so large so quickly? Webb is helping astronomers investigate this mystery in greater detail. By analyzing the spectra of distant galaxies, researchers can identify signatures of actively feeding black holes, regions where gas is being pulled inward and heated to extraordinary temperatures. Some of these signatures appear in galaxies from surprisingly early cosmic epochs. That suggests that black hole growth began very early as well. One possible explanation involves the first generation of massive stars. When those enormous stars collapsed at the ends of their lives, they may have formed relatively heavy black hole seeds. If those seeds began feeding efficiently on surrounding gas, they could grow rapidly. Another possibility involves direct collapse. Under certain conditions, large clouds of gas might collapse directly into black holes without first forming ordinary stars. This process could produce much larger starting points for black hole growth. Both ideas remain active areas of research. What Webb is providing is something extremely valuable: evidence from the universe itself. Instead of relying entirely on theoretical scenarios, astronomers can now observe galaxies from the era when these processes were happening. They can measure the brightness of accreting black holes, the motion of the gas within galaxies, and the chemical composition of the surrounding environment. Each measurement becomes another clue, and together those clues help reconstruct the timeline of cosmic evolution. Perhaps the most remarkable aspect of this work is how quietly the universe reveals its secrets. There are no dramatic explosions visible from Earth when a distant galaxy forms its first generation of stars. No cosmic alarm bells announce the birth of a supermassive black hole. Instead, faint photons travel across billions of years of expanding space. A tiny signal, a whisper of infrared light. When that signal finally reaches the mirrors of the James Webb Space Telescope, it carries with it a story older than our planet. A story of gravity gathering gas, of stars igniting, of galaxies assembling themselves from swirling matter. And what makes Webb so powerful is not only its ability to detect these signals, but also its ability to see extremely faint ones. Earlier telescopes could capture the brightest galaxies from the early universe. Webb can detect objects that are far dimmer, galaxies that may contain only a fraction of the stars in larger systems. This matters because cosmic evolution is not driven solely by the biggest galaxies. Small galaxies may have played an enormous role in shaping the young universe. In particular, astronomers suspect that many faint galaxies contributed to the process of cosmic reionization, the era when the first stars and galaxies gradually ionized the hydrogen filling intergalactic space. Individually, these galaxies may have been modest, but collectively, they could have flooded the universe with ultraviolet radiation strong enough to transform its transparency. Webb's sensitivity allows astronomers to begin detecting these smaller systems. Each new observation adds another piece to the timeline, another marker of how the universe changed as it aged. And when those markers are arranged together, from the faintest distant galaxies to the mature systems closer to us, a remarkable pattern emerges. The universe did not simply appear in its current form. It grew, gradually at first, then more rapidly as structures formed and interacted. Over billions of years, the cosmos transformed from a nearly uniform sea of hydrogen into a vast web filled with galaxies, stars, planets, and complex chemistry. Every deep image captured by Webb now contains evidence of that transformation. Thousands of galaxies, thousands of moments in cosmic time, all visible at once. And when you realize that every one of those distant lights represents a different stage of the universe's history, the night sky becomes something more than scenery. It becomes a living record, a story written in ancient light, a story that we're only now beginning to read clearly, because Webb's mirrors are reaching far enough back to illuminate chapters of cosmic history that were once almost completely hidden from view. When you first hear that Webb can see galaxies more than 13 billion light-years away, it is easy to focus only on the distance. But distance in astronomy is rarely just distance. It is time. Every additional billion light-years is another billion years further into the past. And that means the faint galaxies Webb is detecting are not just far away. They belong to a universe that was fundamentally different from the one we inhabit today. To understand how different, imagine shrinking cosmic history again into that single calendar year. January represents the earliest epochs, when the first stars began igniting inside newly forming galaxies. The universe was still dark in many places, filled with vast clouds of neutral hydrogen. By March and April, star formation accelerates. Small galaxies collide and merge. The first large structures begin assembling along the invisible filaments of the cosmic web. Summer passes as galaxies grow larger and more complex. By autumn, spiral arms begin forming in systems like the Milky Way. Generations of stars enrich the surrounding gas with heavier elements. Winter arrives with planets forming around countless stars. And then, only in the final moments of December 31st, human civilization appears. What Webb is doing, in effect, is looking back toward January and February of that cosmic year, toward the earliest phases of structure building. But here is where something subtle becomes visible. When astronomers compare galaxies across different redshifts, different distances, different ages, they begin to notice patterns that reveal how galaxies change over time. The earliest galaxies tend to be smaller, more compact, more irregular. Their stars are crowded together in dense regions where gas clouds collapsed quickly under gravity. Many of them are intensely blue in colour, which tells us that large numbers of hot, young stars are forming. Blue stars burn bright and fast. They are short-lived compared to stars like our Sun. Their presence indicates a galaxy in the middle of rapid growth. In contrast, many galaxies closer to us, those we see in more recent cosmic eras, contain large populations of older, redder stars. Star formation in those systems has slowed. Much of their gas has already been converted into stars. This gradual shift from young, active galaxies to older, more stable ones is one of the clearest signs of cosmic evolution. But the process is not uniform. Some galaxies grow steadily, others experience dramatic episodes that reshape them entirely. One of the most powerful of these episodes is a starburst. In a starburst galaxy, star formation accelerates dramatically. Instead of producing a few stars each year, the galaxy may create hundreds. This usually happens when gas clouds become compressed, often during galactic mergers or close gravitational encounters. The pressure inside those clouds rises, triggering a cascade of stellar births. Imagine an entire galaxy lighting up with new stars. Massive clusters form. Ultraviolet radiation floods surrounding space. Supernova explosions begin erupting as the most massive stars reach the ends of their brief lives. Webb's infrared instruments are extremely good at detecting these environments because dust heated by young stars glows strongly in infrared wavelengths. In the early universe, starburst activity appears to have been common. Galaxies were interacting frequently. Gas supplies were abundant. Conditions favoured rapid growth. But starbursts also carry consequences. The most massive stars explode as supernovae after only a few million years. Those explosions send shock waves through surrounding gas, sometimes driving material out of the galaxy entirely. Astronomers call these galactic winds. In extreme cases, a galaxy can eject enormous amounts of gas into intergalactic space, temporarily slowing its own star formation. Black holes can contribute to this process as well. When a supermassive black hole feeds actively, the energy released near its event horizon can be enormous. Jets and radiation pouring from the galaxy's center can push gas outward, heating or dispersing it. This feedback helps regulate galaxy growth. Without it, galaxies might convert nearly all of their gas into stars very quickly, leaving little material for future generations. Instead, the interplay between star formation, supernova explosions, and black hole activity creates a kind of cosmic balance. Galaxies grow. They regulate themselves. They evolve. And Webb's observations are beginning to show these mechanisms operating far earlier in cosmic history than we once realized. But perhaps one of the most remarkable aspects of Webb's deep observations is the sheer number of galaxies visible in a single image. When the telescope stares at a small patch of sky, an area no larger than a grain of sand held at arm's length, it can reveal thousands of galaxies. Some appear as faint smudges. Others show surprisingly detailed structures, even at enormous distances. Each one represents an entire galaxy containing billions of stars, and each one belongs to a different moment in cosmic history. Imagine opening a book where every page belongs to a different century. You would not read it from front to back. Instead, you might spread the pages across a table and begin comparing them. What did cities look like in the 1200s? How did architecture change by the 1700s? How did technology evolve by the 1900s? The differences reveal the passage of time. Astronomers perform a similar comparison when analyzing galaxies across redshifts. A galaxy seen 10 billion years in the past shows us one stage of cosmic development. A galaxy seen 5 billion years in the past shows another. A nearby galaxy shows something closer to the present. When these observations are arranged together, they form a sequence, a visual record of how galaxies grow and change. This method does not require waiting billions of years to see evolution happen. The evidence is already in the sky. Different distances reveal different eras, and Webb is extending that timeline farther back than ever before. But the deeper we look into the universe, the more delicate the signals become. The faintest galaxies Webb observes emit incredibly small amounts of light by the time it reaches Earth. That light has travelled across expanding space for billions of years, stretching into infrared wavelengths along the way. Detecting it requires extraordinary sensitivity. Webb's mirror, more than 6 meters across, gathers far more light than previous space telescopes. Its instruments are optimized to detect faint infrared signals that would be invisible to earlier observatories. But even with that technology, observing the earliest galaxies is challenging. Astronomers must separate real signals from background noise. They must confirm distances using precise spectroscopic measurements. They must analyze the shapes, colors, and spectra of galaxies to understand what they are seeing. It is careful work, patient work, and yet, with every year of observations, the picture becomes clearer. The earliest galaxies are no longer theoretical possibilities hidden behind mathematical models. They are objects we can detect, measure, study, in some cases, even map in surprising detail. One of the most powerful examples of this comes from Webb's deep field surveys. In these observations, the telescope stares at one small region of sky for extended periods, collecting light from objects so faint they would otherwise remain invisible. As exposure time increases, more galaxies appear. First the brighter ones, then dimmer systems. Eventually extremely faint galaxies begin to emerge, objects that may represent some of the earlier stages of galaxy formation. The result is an image filled with cosmic history. Nearby galaxies representing recent epochs. Intermediate galaxies showing the universe several billion years ago. Extremely distant galaxies revealing the universe only a few 100 million years after the Big Bang. All of them visible together, all of them part of the same evolving story. And perhaps the most astonishing realization is this. When we observe these galaxies, we are not simply looking at distant objects. We are looking at ancestors. The early galaxies Webb observes eventually merged, grew, and evolved into the structures we see around us today. Some of their stars may still exist in modern galaxies. Some of their heavy elements may now be part of planetary systems orbiting distant suns. The light arriving in Webb's mirrors tonight began its journey before Earth existed. Yet it carries within it the earliest chapters of a story that eventually led to our own presence in the universe. A story written across billions of years, a story that is still unfolding, and as Webb continues its work, the next layers of that cosmic history are beginning to come into focus, revealing not only how galaxies grew, but how the universe itself transformed from a simple beginning into the richly structured cosmos we inhabit today. One of the quiet revelations that emerges from Webb's observations is that galaxies are not isolated stories. They are connected. Every galaxy sits inside a much larger environment. Gas flows along the filaments of the cosmic web. Neighbouring systems tug on one another through gravity. Matter moves slowly but continuously through these enormous structures, shaping how galaxies grow across billions of years. To picture this, imagine rain falling across a vast mountain range. Water gathers in tiny rivulets. Those rivulets join into streams. Streams merge into rivers. Eventually the rivers feed enormous basins. Something similar happens on cosmic scales. The rain in this case is intergalactic gas, drifting through space under the influence of gravity. The mountains and valleys are the invisible gravitational wells created largely by dark matter, and the rivers are the filaments of the cosmic web, guiding matter toward the densest regions. Galaxies grow where those rivers meet. Astronomers sometimes describe these regions as nodes in the cosmic web, places where multiple filaments intersect and matter accumulates. Clusters of galaxies form there. And within those clusters, galaxies continue to interact, merge, and evolve. Webb's observations are beginning to show that these large-scale environments were already shaping galaxies surprisingly early in the universe's history. Some distant galaxies appear grouped together in ways that suggest early cluster formation. These protoclusters are still assembling, but the gravitational foundations are already visible. That tells us something important. Cosmic structure did not emerge slowly from complete disorder. The blueprint was there from the beginning. Those tiny density fluctuations present shortly after the Big Bang, the ones barely detectable in the faint background glow of the universe, were enough to guide the formation of immense structures that would eventually stretch across hundreds of millions of light years. It is almost like watching frost spread across a window. At first the pattern seems random, but as the frost grows, intricate branches begin to appear, forming repeating shapes that extend outward in beautiful complexity. The cosmic web developed in a similar way, though on scales that dwarf anything we encounter in daily life. And inside that growing framework, galaxies were constantly transforming. One of the clearest signs of this transformation is something astronomers call morphological evolution. In simpler terms, the shapes of galaxies change over time. If you look at galaxies in the nearby universe, many of them fall into recognizable categories. Some are spiral galaxies, like our Milky Way, with elegant arms winding outward from a bright central bulge. Others are elliptical galaxies, large and rounded systems where stars move in more random orbits. Still others are irregular galaxies, lacking clear structure. But when astronomers observe galaxies in the distant past, the proportions shift. Spiral structures become less common. Irregular shapes appear more frequently. Galaxies often look clumpier, as though large pockets of star formation dominate their appearance. This suggests that the familiar forms we see in nearby galaxies emerged gradually over cosmic time. Spiral arms, for instance, are delicate gravitational patterns that depend on stable rotational motion within a galaxy's disk. Early galaxies may not have had enough time to settle into such orderly rotation. Instead, they were turbulent environments. Gas clouds collided. Star clusters formed rapidly. Gravity reshaped the galaxy again and again as mergers occurred. Only later, after billions of years of evolution, did many galaxies settle into the calmer, more organized structures we see today. Webb's ability to observe galaxies across different redshifts allows astronomers to trace this transformation in detail. It is like flipping through a time-lapse film of galaxy evolution, except each frame belongs to a different object located at a different distance. Some frames show chaotic beginnings. Others show intermediate stages where structures begin to emerge. And the nearby universe shows the mature forms that developed over billions of years. But the story does not end with stars and gas. Another ingredient plays a crucial role in shaping galaxies: dust. Cosmic dust may sound insignificant, but it has enormous influence on how galaxies evolve. These dust grains are made of elements like carbon, silicon, and iron, materials forged inside stars and released into space through stellar winds and supernova explosions. Over time, dust accumulates within galaxies. It absorbs ultraviolet and visible light from young stars, heating up and re-emitting that energy in infrared wavelengths. This process makes dust-rich galaxies glow strongly in infrared light, exactly the kind of light Webb is designed to observe. By measuring that infrared glow, astronomers can estimate how much star formation is hidden behind thick clouds of dust. In some galaxies, much of the star-forming activity is invisible in ordinary light because dust blocks it. Infrared observations reveal what lies beneath, and Webb is showing that even relatively early galaxies can contain significant amounts of dust. This is another hint that stellar evolution and chemical enrichment may have progressed rapidly in the young universe. Dust is not just a byproduct of star formation. It also influences the next generation of stars. Dust grains help cool collapsing gas clouds by radiating energy away. This cooling allows gas to compress more easily, making it easier for gravity to form new stars. Dust also plays a crucial role in planet formation. In disks of gas and dust surrounding young stars, tiny grains collide and stick together, gradually forming larger particles. Over time, those particles can grow into planetesimals, the building blocks of planets. In other words, dust links the evolution of galaxies to the eventual formation of planetary systems. When Webb detects dust in galaxies billions of light-years away, it is observing the early steps in a chain of processes that can eventually produce worlds. Worlds with oceans, worlds with atmospheres, possibly even worlds with life. Of course, most of those distant galaxies are far too young for such outcomes to have occurred yet, but the ingredients are already appearing. The heavy elements, the dust grains, the chemical complexity required for planetary systems, and this realization carries a quiet emotional weight. Because the light Webb collects tonight left those galaxies when the universe was still in its early phases of growth. The atoms that now form your body were not yet assembled into planets. Earth did not exist. Our sun had not formed. Yet the processes that would eventually lead to those things were already underway. Stars were forging elements. Supernovae were scattering them across space. Galaxies were mixing and recycling that material again and again. Cosmic evolution was building the raw materials of future worlds. When we look at distant galaxies with Webb, we are seeing the earliest stages of that long preparation. It is easy to think of astronomy as distant and abstract, but the story written in those faint galaxies leads directly to us. Every carbon atom in your cells was once inside a star. Every oxygen atom you breathe was created in stellar fusion billions of years ago. The universe did not begin with those elements. It learned how to make them. And it learned early. The deeper Webb looks into cosmic history, the clearer it becomes that the universe began building complexity surprisingly quickly. The earliest galaxies were not empty frameworks waiting for the distant future. They were active, creative environments. Stars ignited. Black holes grew. Chemical elements spread through interstellar space. And over time, the vast cosmic web carried that enriched material into larger and larger structures. What we see today, the galaxies, the stars, the planets, is the result of countless generations of cosmic change. But Webb's greatest gift may be the perspective it gives us on that process. For the first time, we are seeing the universe not as a static stage filled with distant objects, but as something that has been evolving continuously for nearly 14 billion years. A story unfolding across unimaginable spans of time. And every new observation pushes us a little farther back into those early chapters, toward the moment when the first galaxies began lighting the darkness, and the universe itself was just beginning to discover what it could become. There is something quietly astonishing about the fact that the universe keeps its own history so faithfully. Not in books, not in archives, but in light. Every photon that reaches a telescope carries information about the conditions where it began, the temperature of the gas it passed through, the elements present in distant stars, the expansion of space during its journey, even the gravitational fields it encountered along the way. For billions of years, those photons travel outward in all directions. Most will never meet anything again, but a tiny fraction eventually arrive at a mirror like the one carried by the James Webb Space Telescope. When that happens, an ancient message is received. And the message is surprisingly detailed. One of the ways astronomers decode it is through the subtle stretching of light caused by the expansion of the universe. As galaxies recede from one another, the wavelengths of light travelling between them are stretched. Blue light becomes redder. Red light slides into infrared. The farther a galaxy lies, the more its light has been stretched. This stretching provides a kind of cosmic timestamp. By measuring how far the spectral lines of elements have shifted toward longer wavelengths, astronomers can determine the galaxy's redshift. And redshift corresponds directly to how long that light has been travelling. It is a way of measuring age using distance. Webb's instruments are designed with this in mind. They do not simply photograph galaxies. They measure their spectra with remarkable precision, revealing patterns of absorption and emission that act like fingerprints. A single spectrum can tell astronomers the galaxy's distance, the elements present within it, the temperature of its gas, and sometimes even the motion of stars and clouds inside the system. This level of detail matters because it transforms faint smudges of light into physical objects with histories. You can think of it as the difference between seeing a silhouette and hearing someone speak. The outline gives you shape, the voice gives you identity. And Webb is listening carefully to the voices of galaxies that lived when the universe was very young. When astronomers began examining these spectra from the earliest galaxies Webb detected, they noticed something both exciting and puzzling. Some galaxies seem to have extremely intense emission lines, signals produced when gas is heated by powerful sources of energy, usually young stars or actively feeding black holes. The strength of those signals suggests that early galaxies may have contained unusually dense star-forming regions. Imagine entire clusters of massive stars igniting within a relatively small space. Their ultraviolet radiation would flood surrounding gas clouds, heating them and causing them to glow brightly at specific wavelengths. The result is a galaxy that shines with characteristic spectral lines far stronger than those typically seen in the modern universe. This fits with another pattern astronomers are beginning to see. Early galaxies may have been incredibly efficient star factories. In modern galaxies like the Milky Way, star formation happens at a moderate pace. Gas clouds collapse gradually, producing new stars over long timescales. But in the early universe, the conditions were different. Gas densities were higher. Interactions between galaxies were more common. Gravitational disturbances stirred interstellar material, compressing clouds and triggering bursts of star formation. Instead of a slow, steady process, many galaxies experienced rapid construction phases. Stars formed quickly, mass accumulated rapidly, and because massive stars live short lives, their death soon enriched surrounding gas with heavy elements. This accelerated cycle could explain why some distant galaxies appear more chemically evolved than expected. They may have gone through several generations of stars in a relatively short period of cosmic time, each generation contributing new elements. Each generation reshaping the galaxy's internal environment. And as this process unfolded across billions of galaxies throughout the young universe, the chemistry of the cosmos began to change. The first galaxies were dominated by hydrogen and helium. Later generations contained increasing amounts of carbon, oxygen, silicon, and iron. Eventually, those elements formed dust grains, rocky planets, and complex molecules. Seen across the entire observable universe, it resembles a vast chemical evolution. The cosmos learning how to build complexity. Webb's infrared capabilities are especially important for tracing this process, because many of the key spectral lines used to identify elements in distant galaxies have been shifted out of visible wavelengths. For galaxies at extremely high redshift, the signatures of oxygen or hydrogen that once appeared in ultraviolet light now arrive in the infrared. Without a telescope sensitive to those wavelengths, they would remain hidden. This is one of the reasons Webb represents such a major step forward in our ability to study the early universe. It is not simply taking sharper pictures. It is opening windows into eras that were previously invisible. And when those windows open, the universe sometimes surprises us. One example involves galaxies that appear extraordinarily compact yet extremely luminous. Their stars seem packed into regions far smaller than the disks of modern spiral galaxies. This means that enormous numbers of stars are forming within relatively tight volumes of space. The resulting environments must be incredibly energetic. Radiation from massive stars floods the surrounding gas. Supernova explosions occur frequently as those stars reach the ends of their short lives. Shock waves propagate through the galaxy, stirring gas and triggering further star formation. It is a feedback loop of cosmic construction. But such dense activity cannot continue forever. Eventually, the intense energy produced by massive stars and black holes begins pushing gas outward. Some galaxies may lose large fractions of their gas this way, slowing their growth. Others may later acquire new gas flowing along cosmic filaments, reigniting star formation. This ongoing exchange of matter between galaxies and the intergalactic medium is another key aspect of cosmic evolution. Galaxies are not closed systems. They breathe. Gas flows in, gas flows out. Elements forged in stars are carried into surrounding space, where they may later become part of other galaxies or future generations of stars. The cosmic web acts like a network of arteries and veins, circulating matter across enormous distances. Webb's observations are beginning to reveal this circulation in action. Some distant galaxies show extended halos of glowing gas surrounding their central regions, evidence of material being pushed outward by stellar winds or black hole activity. Other galaxies appear embedded within streams of gas that may be flowing inward along cosmic filaments. These gas flows help determine how galaxies grow. Without fresh gas, star formation eventually slows. With abundant inflow, galaxies can sustain star formation for billions of years. The balance between these processes shapes the entire life cycle of galaxies. And because Webb can observe galaxies across such a wide range of cosmic time, astronomers can begin tracing how these gas flows change as the universe ages. Early galaxies appear to be surrounded by enormous reservoirs of gas, providing ample fuel for rapid growth. Later galaxies gradually exhaust or disperse much of that supply. Star formation slows. Structures stabilize. The universe matures. When you step back and look at the larger picture emerging from these observations, it begins to resemble something surprisingly familiar. A living ecosystem. Matter moves. Energy flows. Structures grow, interact, and transform. Over time, complexity emerges from simpler beginnings. The difference, of course, is scale. This ecosystem spans billions of light years. Its cycles unfold over billions of years. And yet, the same fundamental forces operate everywhere: gravity, radiation, chemistry. The James Webb Space Telescope has not changed those forces. What it has changed is our ability to see them operating in the earliest phases of cosmic history. We are no longer limited to studying the mature universe around us. Now we can watch the formative stages as well. The first galaxies lighting up the cosmic web. The first generations of stars forging heavy elements. The earliest black holes beginning to grow. Each new observation extends the timeline. Each faint galaxy pushes our view closer to the moment when the universe transitioned from darkness into light. And with every step deeper into that past, the realization becomes clearer. The universe did not begin as the richly structured cosmos we see today. It became that way, slowly, relentlessly, across billions of years of evolution written in ancient light. There is a moment, when you stare long enough at one of Webb's deep images, when the sheer number of galaxies begins to feel almost unreal. At first you see only a few bright ones. Then your eyes adjust. Tiny smudges appear everywhere, each one a distant galaxy, each containing billions of stars. Some are near enough that their spiral arms can be seen faintly curling around luminous centers. Others are so far away that they appear as little more than reddish dots. Yet every one of them is an entire cosmic system. If you held a grain of sand between your fingers at arm's length, the patch of sky it covers might contain thousands of galaxies like these. The universe is so vast that even its seemingly empty regions are filled with structures spread across unimaginable distances. But what makes these Webb images so powerful is not just the number of galaxies. It is the timeline they represent. In a single frame, you are looking at billions of years of cosmic evolution layered together. Some galaxies in the image may be relatively nearby, their light beginning its journey when dinosaurs still walked on Earth. Others may belong to an era when our solar system had not yet formed. Still others appear when the universe itself was only a few 100 million years old. It is like standing in a gallery where each painting was created in a different century. At first glance, they all share a common theme. But look more closely, and the subtle changes reveal the passage of time. Early galaxies tend to be smaller. Their shapes are often irregular, dominated by bright clumps of star formation. They look restless, as though gravity is still gathering their material into more stable forms. Galaxies closer to our own time appear calmer. Their structures are smoother. Spiral arms wind gracefully through rotating disks. Elliptical galaxies glow with the soft light of billions of older stars. This contrast between early turbulence and later stability is one of the clearest patterns astronomers observe when comparing galaxies across cosmic time. And Webb is now revealing that transition with extraordinary clarity. But there is another aspect of these observations that deserves attention. The universe is not simply aging. It is also slowing down. In the early epochs, star formation across the cosmos was far more intense than it is today. Astronomers sometimes refer to this period as the cosmic noon, when galaxies were producing new stars at their peak rates. If you could travel back roughly 10 billion years, you would see galaxies blazing with star formation. Massive blue stars would illuminate swirling gas clouds. Supernova explosions would punctuate the darkness as those stars reached the ends of their brief lives. Compared to that era, the present-day universe feels quieter. Many galaxies, including our own, have entered a slower phase of evolution. The raw fuel for star formation, cold hydrogen gas, has gradually been used up or expelled. Without that fuel, new stars form more slowly. This does not mean the universe has stopped evolving, but the pace has changed. Imagine a forest after the most intense period of growth has passed. The largest trees remain, their canopies spreading wide. Young saplings still appear here and there, but the explosive expansion of earlier years has faded. The same pattern appears in galaxies. The early universe was filled with rapid construction. The modern universe shows the mature results. Webb's observations help connect these two phases by revealing how galaxies transition from one stage to the other. One clue lies in the motion of gas inside galaxies. When astronomers analyze spectral lines from distant galaxies, they can measure subtle shifts caused by the motion of gas clouds. These shifts reveal whether gas is rotating smoothly, falling inward, or being pushed outward. In many early galaxies, the gas appears turbulent. Instead of orderly rotation, it moves chaotically, likely stirred by mergers, gravitational disturbances, and intense bursts of star formation. Over time, as galaxies grow larger and interactions become less frequent, their internal motions begin to settle. Disks form. Rotation stabilizes. Spiral patterns emerge. The chaotic youth of galaxies gradually gives way to more organized structures. But not every galaxy follows the same path. Some galaxies experience violent transformations that permanently alter their appearance. Consider what happens during a major galactic merger. When two galaxies of comparable size collide, their gravitational forces tear stars from their original orbits. Vast tidal streams stretch outward into space, forming luminous arcs that can span hundreds of thousands of light years. Gas clouds collide head-on, compressing and heating the material. A burst of star formation ignites across the merging system. Eventually, the two galaxies lose their distinct identities, blending into a single, larger structure. Often the result is an elliptical galaxy, smooth, rounded, filled with older stars whose orbits are no longer confined to a disk. Webb has captured glimpses of such interactions in distant galaxies. Even billions of years in the past, gravitational encounters were reshaping galaxies across the cosmos. In fact, mergers were likely far more common then than they are today. Because the universe was smaller, galaxies lived closer together. Gravity had an easier time pulling them into interactions. These cosmic collisions played a crucial role in building larger galaxies over time. Our own Milky Way carries traces of this history. Streams of stars orbiting in its outer halo are believed to be remnants of smaller galaxies that were absorbed long ago. Their stars now move through the Milky Way like archaeological artifacts of ancient mergers. The same process is happening throughout the universe. Galaxies grow not only by forming stars from their own gas, but also by incorporating the material of their neighbours. This gradual accumulation of mass is sometimes called hierarchical growth. Small systems form first. Then they merge to create larger ones. Clusters of galaxies eventually assemble from many smaller groups. The cosmic web becomes richer and more interconnected. And across billions of years, these interactions transform the appearance and behaviour of galaxies. Webb's ability to observe galaxies across enormous spans of cosmic time allows astronomers to test this picture directly. They can look at distant galaxies and ask, are mergers already happening? Are galaxies already forming groups? Are black holes already influencing their surroundings? Increasingly, the answer appears to be yes. Even in the early universe, gravity was hard at work building structure. Small galaxies were gathering into larger systems. Gas flowed along cosmic filaments toward growing clusters. Stars were forming and dying, enriching the surrounding gas with heavier elements. It is easy to think of the universe as static because the sky changes so slowly on human timescales. But Webb reminds us that the cosmos has always been dynamic. Galaxies are not permanent fixtures. They are evolving systems. Stars are born. Stars die. Black holes grow. Gas circulates. Structures merge and reshape themselves. And all of this has been happening for nearly 14 billion years. The faint red galaxies Webb observes are not relics frozen in time. They are moments within that long transformation. Moments when the universe was experimenting with new structures, new chemistry, new possibilities. Every deep observation pushes our view farther back along that timeline. And the deeper we look, the closer we come to a remarkable threshold. The point where the first galaxies appeared and the universe began emerging from the long darkness that followed the Big Bang. That transition, when the earlier stars ignited and began lighting the cosmic web, may be one of the most important chapters in the entire history of the universe. And thanks to Webb's extraordinary reach, we are now approaching it more closely than ever before. There was a time when the universe contained no galaxies at all. No spiral arms, no clusters of stars. No glowing nebulae scattered through interstellar space. After the Big Bang, the cosmos was filled mostly with hydrogen and helium gas. The temperature was still high, and matter was spread remarkably evenly across space. Tiny fluctuations in density existed, but they were incredibly small, barely noticeable ripples in an otherwise smooth sea of particles. For millions of years, the universe expanded and cooled. Gravity slowly began amplifying those faint ripples. Regions that were slightly denser than average pulled in surrounding matter. Over time, those regions grew stronger, gathering more gas and dark matter into expanding gravitational wells. But for a long stretch of cosmic time, there were still no stars. Astronomers sometimes call this period the Cosmic Dark Ages, not because the universe was completely black. There was still faint radiation left over from the Big Bang, but because no luminous objects had formed yet. There were no stars to shine, no galaxies to illuminate the expanding darkness. Imagine standing on a planet during a night before the first sunrise ever occurred. That is something like what the universe was experiencing then. Darkness filled the cosmic landscape while gravity quietly prepared the conditions for what would come next. Eventually, the first gas clouds collapsed. Inside those clouds, gravity squeezed hydrogen atoms closer and closer together. Temperatures rose, pressure increased. And in a few of the densest regions, nuclear fusion ignited. The first stars were born. These stars were likely very different from the ones we see today. Without heavy elements to cool the collapsing gas, the earlier stars may have grown extremely massive. Some models suggest that many of them were dozens or even hundreds of times heavier than the Sun. Massive stars burn fiercely. They shine with intense ultraviolet radiation and exhaust their fuel quickly. Instead of lasting billions of years like our Sun, many early stars may have lived only a few million years before collapsing or exploding. But during their brief lives, they transformed the universe. Their radiation began ionizing the surrounding hydrogen gas, stripping electrons from atoms and gradually making the cosmos more transparent to light. Their deaths forged heavy elements that had never existed before. Carbon, oxygen, iron, the first steps in a long chain of chemical enrichment that would eventually make planets and life possible. This transition from darkness to light is one of the most dramatic turning points in cosmic history. And remarkably, the James Webb Space Telescope is now beginning to detect galaxies from that era. Not the very first stars themselves. Those individual objects are far too faint and distant to observe directly with current instruments, but the earliest galaxies formed from their descendants. When Webb identifies galaxies whose light began travelling toward Earth more than 13 billion years ago, it is seeing systems that existed only a few 100 million years after the Big Bang. These galaxies are among the first structures to illuminate the cosmic web, and their existence tells us something profound. The universe did not remain dark for long. Gravity worked quickly, Gas gathered rapidly. Stars ignited earlier than we once believed. But detecting these galaxies is extremely challenging. Their light has travelled so far that the expansion of the universe has stretched it dramatically. What began as ultraviolet radiation from young stars arrives at Earth today as faint infrared light. Without Webb's sensitivity to infrared wavelengths, these signals would remain hidden. Even with Webb, astronomers must search carefully. The earliest galaxies appear incredibly faint and often extremely small in the telescope's images. Many of them are barely distinguishable from background noise until their spectral signatures are analysed. But once confirmed, they become markers of cosmic time. Each one reveals how early galaxy formation began. Each one tells us how quickly stars started shaping the universe. And the more of them astronomers discover, the clearer the timeline becomes. Some of the galaxies detected by Webb appear when the universe was only about 300 million years old. That may sound like a long time, but on cosmic scales it is astonishingly early. If the entire 13.8 billion year history of the universe were compressed into a single day, 300 million years would correspond to just a few minutes after midnight. Within that brief window, gravity had already gathered matter into structures large enough to host entire galaxies. Stars had already formed. Some had already lived and died. Heavy elements had already begun spreading into surrounding gas. The universe wasted no time. And yet, even as these discoveries deepen our understanding, they also raise new questions. How exactly did the first galaxies assemble so quickly? Did the earliest gas clouds collapse faster than expected? Did dark matter halos provide especially efficient gathering points for matter? Were the first stars even more massive than current models predict? These are the kinds of questions astronomers are now exploring using Webb's data. The telescope is not rewriting the laws of physics. Gravity still behaves the same way. The expansion of the universe still follows the patterns predicted by cosmology. But Webb is providing new observations that refine our understanding of how quickly those laws produced the structures we see today. Sometimes the universe turns out to be more efficient than our models anticipated. Sometimes processes begin earlier than we expected. And sometimes entirely new details appear once we finally gain the ability to observe them. That is the quiet power of better instruments. They do not change reality. They reveal it more clearly. In Webb's case, the clarity comes from its ability to see faint infrared light across extraordinary distances. Every time it detects a galaxy from the early universe, it adds another data point to the map of cosmic evolution. A marker showing when star formation began, a clue about how galaxies grew, a glimpse of the universe learning to build structure. And when astronomers assemble all those clues together, from nearby galaxies to the most distant ones, they can begin tracing the full arc of cosmic history. From the first stars emerging from darkness, to galaxies forming and merging, to clusters assembling along cosmic filaments, to the richly structured universe we see today. It is a story written across billions of years. But for the first time, we are beginning to see enough of the early chapters to understand how the narrative truly begins. The James Webb Space Telescope is not watching the universe evolve in real time. The changes are far too slow for that. What it is doing is something almost as extraordinary. It is allowing us to see multiple ages of the universe at once. A cosmic timeline spread across the sky. Ancient galaxies revealing the earliest moments of structure. Younger galaxies showing intermediate stages of growth. Nearby galaxies representing the present era of cosmic maturity. Each one a snapshot from a different chapter. Each one part of a continuous story of evolution written in light that has been travelling across space for billions of years. And when you begin to see the sky this way, something subtle changes in how the universe feels. The stars overhead are no longer just distant lights. The galaxies captured in Webb's deep images are no longer just faint smudges scattered across darkness. They become moments. Moments from different eras of the same unfolding story. A nearby galaxy might show the universe as it was a few 100 million years ago. Another, slightly dimmer and redder, might belong to a time billions of years earlier. A tiny infrared point near the edge of Webb's sensitivity might be revealing a galaxy that existed when the universe was still in its earlier stages of growth. Together they form a sequence. Not arranged neatly in order, but present all at once, like photographs from different decades scattered across a table. Astronomers have learned to read that scattered collection as a timeline And one of the most fascinating things that timeline reveals is how dramatically the universe has changed. Consider the distribution of star formation. Today, most galaxies produce new stars at relatively modest rates. The Milky Way forms roughly 1 or 2 stars each year. That may sound impressive, but on cosmic scales it is a calm pace. Billions of years ago, galaxies were far more active. Entire regions of the universe were blazing with star formation. Massive blue stars were forming rapidly, flooding surrounding space with ultraviolet radiation. These stars burned through their fuel quickly and exploded as supernovae, scattering heavy elements back into interstellar space. The cycle repeated again and again. Gas collapsed. Stars ignited. Stars died. New generations formed from the enriched material. This constant recycling gradually changed the chemical composition of the universe. At first there were almost no heavy elements at all. Then carbon and oxygen began appearing. Later came silicon, iron, and other elements forged in the most violent stellar explosions. Over billions of years, the cosmic environment became richer in the ingredients needed for planets and complex chemistry. Webb's observations allow astronomers to trace that chemical evolution directly. By examining the spectral fingerprints of distant galaxies, they can measure how the abundance of heavy elements changes across cosmic time. Early galaxies tend to contain fewer heavy elements. Later galaxies contain more. The pattern is exactly what we would expect if generations of stars were gradually enriching the universe. But the speed of that enrichment appears to be faster than once imagined. Some galaxies observed relatively early in cosmic history already show surprising amounts of oxygen and carbon. That means multiple generations of stars must have formed, lived, and exploded before the light we now detect even began its journey toward Earth. In other words, stellar evolution was already well underway. The universe was building complexity rapidly, and this process was happening across countless galaxies at once. When Webb stares at a deep field image, every faint red dot represents a separate site of cosmic activity. Each galaxy contains billions of stars. Each star has its own life cycle. Multiply that by thousands of galaxies in a single image, and you begin to glimpse the scale of cosmic evolution unfolding across the universe. It is almost impossible for the human mind to grasp fully, but certain patterns begin to stand out. Galaxies grow larger over time. Their internal structures become more organized. Star formation gradually slows as gas supplies are consumed or expelled. Heavy elements accumulate, allowing more complex chemistry to emerge. And the cosmic web itself becomes more defined as gravity continues shaping matter into filaments, clusters, and enormous voids. This grand transformation did not happen suddenly. It unfolded step by step across billions of years. And because light takes time to travel, telescopes like Webb allow us to see many of those steps simultaneously. A galaxy 10 billion light-years away shows one stage of development. A galaxy 5 billion light-years away shows another. A nearby galaxy shows something closer to the present moment. Together they reveal a sequence that would otherwise take billions of years to observe. It is as though the universe has arranged its own history across the sky. All we had to do was build instruments capable of reading it. And yet, there is still another layer to this story. Because galaxies themselves are not the final stage of cosmic evolution. Inside galaxies, new structures continue forming. Stars create planetary systems. Planets develop atmospheres. Chemical reactions become more complex. In at least one corner of the universe, those reactions eventually produced life. That connection may seem distant when we are discussing galaxies billions of light-years away, but the link is real. The carbon in your body was once inside a star. The oxygen in the air you breathe was forged through nuclear fusion deep within stellar cores. Those elements were scattered across space by ancient supernova explosions long before the sun existed. Over time, they became part of the gas clouds that eventually formed our solar system. And those clouds were themselves shaped by the long history of cosmic evolution unfolding throughout the Milky Way. In other words, the same processes Webb is now observing in distant galaxies helped create the ingredients for our own existence. The story of cosmic evolution is not just about galaxies. It is also about the origins of the elements that make planets possible. The origins of chemistry, the origins of life, and perhaps the most extraordinary aspect of this realization is the timing. The universe has existed for about 13.8 billion years. For most of that time, there were no observers. no telescopes, no minds capable of wondering how the cosmos came to be. Stars formed and died. Galaxies collided and merged. Black holes grew quietly in the centers of galaxies. All of it unfolded without witness. Only recently, within the last tiny fraction of cosmic history, has a species emerged that can study these processes. A species capable of building instruments like the James Webb Space Telescope. A species capable of intercepting ancient light that began traveling toward Earth billions of years ago, and understanding what it means. When Webb detects a faint galaxy whose light began its journey more than 13 billion years ago, that light left its source long before our planet existed. It travelled across expanding space for nearly the entire age of the universe. And tonight, it arrives in the mirror of a telescope built by beings made of the very elements those ancient stars helped create. There is a quiet symmetry in that. The universe evolving for billions of years until it eventually becomes capable of observing its own history. But even with Webb's extraordinary capabilities, we have not yet reached the earliest possible limits of observation. Beyond the most distant galaxies we can currently detect lies an even earlier frontier, a time when the first stars were just beginning to ignite, a time when the cosmic web was still forming its earliest filaments, a time when the universe was only beginning its long transformation from simplicity into the vast, structured cosmos we see today. And as Webb continues to observe deeper and longer, astronomers are slowly approaching that frontier. Each new discovery pushes the boundary slightly farther back, closer to the moment when the first lights of the universe flickered on, closer to the moment when the long darkness after the Big Bang finally began to give way to the glow of stars spreading across the cosmic web, closer to the beginning of the story that eventually led, billions of years later, to us looking back and trying to understand how it all began. There is a quiet limit to how far back any telescope can see. Not because the instruments lack power, and not because the universe suddenly stops beyond a certain distance, but because the early universe itself once prevented light from travelling freely. Before the first stars formed, space was filled with neutral hydrogen gas. Hydrogen atoms are remarkably effective at absorbing certain wavelengths of light, especially ultraviolet radiation. When photons attempted to travel through this fog-like medium, many were scattered or absorbed before they could move very far. In those early eras, the universe was not completely opaque, but it was far less transparent than it is today. The situation gradually changed as the first generations of stars began shining. Their intense ultraviolet radiation started ionizing the surrounding hydrogen. Electrons were stripped away from atoms, transforming neutral gas into plasma. Ionized gas interacts differently with light, allowing photons to travel much greater distances without being absorbed. Slowly, the cosmic fog lifted. This transition, known as cosmic reionization, was one of the most important transformations in the history of the universe. It did not happen all at once. Instead, pockets of ionized gas began forming around the earliest galaxies. Each galaxy acted like a lantern in the darkness, carving out a small transparent bubble in the surrounding hydrogen. As more galaxies formed, those bubbles expanded. Eventually they began overlapping. Over hundreds of millions of years, the universe transformed from a patchwork of glowing islands in a dark ocean into a largely transparent cosmic landscape where light could travel freely across enormous distances. Understanding how and when this process occurred has been a major goal of modern astronomy. And the James Webb Space Telescope is now providing some of the most detailed clues yet. By identifying galaxies that existed during the era of reionization, astronomers can estimate how much radiation these early systems produced. The brightness of those galaxies, combined with their abundance, helps determine whether they could have generated enough energy to ionize the surrounding hydrogen. So far, the emerging picture suggests that the process may have been driven largely by many small galaxies rather than a few extremely bright ones. Individually, these galaxies were modest, but together they formed a vast network of light sources scattered across the cosmic web. Think again of a dark landscape at night. At first, only a few distant lights appear. Then more lights begin to flicker on across hills and valleys. Small towns illuminate their streets. Houses glow with windows lit from within. Gradually the darkness recedes, not because a single brilliant beacon appears, but because countless smaller lights combine to illuminate the landscape. Cosmic reionization may have unfolded in much the same way, and Webb is now detecting many of those early lights. Some of the galaxies it observes appear incredibly faint and compact, yet their presence suggests that star formation was already widespread. Even small galaxies were contributing to the growing glow of the young universe. But detecting these systems requires extraordinary patience. When Webb observes the most distant galaxies, the telescope must collect light for long periods, sometimes many hours or even days, to gather enough photons for reliable measurements. The signals are faint. A distant galaxy might deliver only a tiny trickle of photons to Webb's detectors each second. Yet those few photons carry invaluable information. They reveal the galaxy's distance through redshift. They reveal the composition of its gas through spectral lines. They reveal the presence of star formation or black hole activity through distinctive emission patterns. In a sense, astronomers are reconstructing the early universe photon by photon. Each observation adds a small piece to the puzzle. Over time, those pieces assemble into a clearer image of how the cosmos evolved during its earlier stages. One of the remarkable things about this process is that it continues to produce surprises. Some galaxies detected by Webb appear brighter than expected for their distance. Others appear to contain large amounts of dust, even though the universe was still young. There are hints that certain galaxies may have formed stars at astonishing rates, converting gas into stellar populations with extraordinary efficiency. None of these discoveries overturn our basic understanding of cosmic evolution, but they do remind us that the universe often turns out to be more creative than our initial models suggest, and that creativity becomes visible only when our instruments grow sensitive enough to detect it. In the past, astronomers could study the nearby universe in great detail but could only glimpse the earliest galaxies faintly. Now the situation is beginning to reverse. With Webb, the young universe is becoming visible in unprecedented clarity. We can see galaxies forming during the first billion years. We can measure their chemical compositions. We can analyze their star-forming activity. We can begin mapping the distribution of early structures along the cosmic web. In other words, the earliest chapters of cosmic history are slowly coming into focus. And those chapters reveal a universe that wasted very little time building complexity. Gravity gathered matter into structures quickly. Stars ignited early. Heavy elements began appearing surprisingly soon after the first galaxies formed. Black holes were already beginning to grow in the centers of galaxies. What once seemed like a slow and gradual process now appears more energetic and dynamic. The young universe was busy. It was assembling galaxies, forging elements, and reshaping matter across enormous distances, all while expanding steadily outward. Every distant galaxy Webb observes is a witness to that activity. A witness whose light has been traveling toward us for nearly the entire lifetime of the cosmos. When those ancient photons finally reach Webb's mirrors, they bring with them evidence of events that occurred billions of years ago. Events that helped transform the universe from a simple mixture of hydrogen and helium into the rich, structured cosmos we see today. But there is another realization that emerges as astronomers continue studying these early galaxies. Even though we can now observe objects from extremely early cosmic eras, the universe itself still extends far beyond what we can ever see. Light from the most distant galaxies we detect today has taken more than 13 billion years to reach us. Yet during that time, the universe has continued expanding. Those galaxies are now far farther away than the distance their light travelled. Beyond them lie regions whose light has not yet had time to reach Earth. And beyond those regions, the universe may continue indefinitely. The observable universe, the portion we can see, is therefore only a bubble within a much larger cosmic expanse. A bubble defined by the distance light has been able to travel since the beginning of cosmic time. Inside that bubble lies the entire story we can observe: the formation of galaxies, the birth and death of stars, the growth of cosmic structure. And thanks to the James Webb Space Telescope, we are now reading that story with greater clarity than ever before, because its mirrors are capturing the faintest whispers of light from the earliest epochs of cosmic evolution. When you step back from the individual discoveries, the distant galaxies, the spectral lines, the faint infrared smudges detected at the edge of visibility, something larger begins to emerge. A pattern. Not just a pattern of objects scattered through space, but a pattern of change unfolding across time. For centuries, humans looked at the night sky and saw permanence. The stars appeared fixed. The constellations seemed eternal. Even galaxies, once we discovered them, felt like distant islands that had always existed exactly as they are now. The deeper truth is very different. The universe has been changing from the beginning. Stars are born and die, galaxies grow and merge, black holes expand, chemical elements spread and accumulate. And these transformations do not occur randomly. They follow physical processes that repeat again and again across cosmic history. Gravity gathers matter, gas collapses, fusion ignites, radiation pushes outward, supernova scatter elements into surrounding space. New stars form from the enriched material. Over billions of years, these cycles gradually reshape the cosmos. What Webb has done is allow us to see multiple stages of that transformation at once. Instead of studying only the mature universe around us, we can now compare galaxies from vastly different eras. A galaxy 13 billion light-years away shows us the universe near its beginning. A galaxy 5 billion light-years away shows us an intermediate stage. Nearby galaxies reveal the later chapters of cosmic evolution. Placed together, they form something like a time-lapse sequence. But this sequence is not arranged in order. It is scattered across the sky. Astronomers reconstruct it by measuring distances, analysing spectra, and carefully comparing galaxies that lived at different points in cosmic history. And the result is a picture of the universe not as a static object, but as an evolving system. This realization has profound consequences, because once you begin seeing the cosmos as something that evolves, every observation becomes part of a larger narrative. A faint galaxy detected by Webb is not just a distant object. It is a stage in a process, a snapshot from a time when galaxies were still learning how to assemble themselves. The same is true for stars. The earliest stars likely formed under conditions very different from those we see today. Their enormous masses and short lifetimes meant they transformed the surrounding universe quickly. Later generations of stars formed in environments already enriched with heavier elements. Planetary systems became possible. Rocky worlds began appearing around young stars. In this way, cosmic evolution is also chemical evolution. The universe did not begin with the ingredients needed for planets, oceans, or living organisms. It created them gradually. Every generation of stars added new elements to the cosmic inventory. And over billions of years, that inventory became complex enough for entirely new kinds of structures to emerge. Planets, atmospheres, organic molecules, eventually life. Seen from this perspective, Webb's observations are not just about distant galaxies. They are about origins, because the earliest galaxies are where many of the processes that shaped the later universe began. They forged the first heavy elements. They triggered cycles of star formation that enriched interstellar gas. They built the structural framework from which later galaxies, including our own, would eventually grow. When Webb observes these galaxies, it is watching the early stages of a chain reaction that extends all the way to the present day. But the telescope also reveals something else, a sense of proportion. Human history spans only a few thousand years of recorded time. Civilizations rise and fall within centuries. Even the entire history of our species occupies only a tiny fraction of cosmic time. The universe was already billions of years old before Earth formed. It was already filled with galaxies, stars, and heavy elements. And yet, despite that enormous span of time, we now find ourselves living at a moment when it has become possible to study the universe's earliest chapters directly. This is not something that would have been possible even a few decades ago. For most of human history, the distant universe was invisible. Early telescopes revealed nearby planets and stars. Later instruments discovered galaxies. But the earliest epochs of cosmic history remained hidden behind the limits of our technology. Now those limits are shifting. With Webb's infrared sensitivity, astronomers are detecting galaxies from the first few 100 million years after the Big Bang. They are measuring their chemical composition. They are analysing how quickly they formed stars. They are searching for the earliest signs of black hole growth. Each new observation extends the cosmic timeline a little farther back. Each new discovery refines our understanding of how quickly the universe transformed from simplicity into complexity. But perhaps the most remarkable aspect of this work is how quietly it unfolds. There are no sudden flashes visible to the naked eye when a new early galaxy is discovered. No cosmic fanfare announces that a photon has finally arrived after travelling for 13 billion years. Instead, astronomers sit at computers. They analyze faint patterns in spectra. They compare models with observations. They slowly piece together the story hidden inside those ancient signals. It is patient work, but the rewards are extraordinary, because every time a new galaxy from the early universe is confirmed, it becomes another marker in the timeline of cosmic evolution. Another point showing when stars began forming. Another clue revealing how quickly galaxies assembled. Another glimpse of the universe in the act of becoming what it is today. And the deeper Webb looks, the more detailed that timeline becomes. Already, the telescope has identified galaxies from remarkably early epochs, some appearing less than 400 million years after the Big Bang. These discoveries are pushing our understanding of cosmic history closer and closer to its beginning. Yet there is still a boundary. Even Webb cannot see the first stars directly. Those earliest objects remain just beyond the reach of current telescopes. But their influence is visible. Their descendants form the earliest galaxies we can observe. Their supernova explosions seeded the cosmos with heavy elements. Their radiation helped lift the fog of neutral hydrogen during the era of reionization. In that sense, the first stars are like the opening lines of a story whose later chapters we can read clearly. We may not see them directly yet, but their effects ripple through the universe that followed. And as Webb continues to observe the sky, hour after hour, night after night, it keeps collecting the faint signals that bring those ancient chapters into sharper focus. Each photon that reaches its mirrors carries a fragment of history, a message sent billions of years ago, a record of how galaxies grew, how stars forged elements, and how the universe slowly transformed itself across unimaginable spans of time. And when we gather those fragments together, something extraordinary becomes clear. The sky is not simply a view into space. It is a view into time, a vast cosmic archive filled with light that has been travelling for billions of years, waiting for a moment when someone might finally notice what it has been carrying all along. Once you truly understand that the sky is a timeline, it becomes difficult to see it the same way again. The stars overhead no longer feel like decorations scattered across darkness. Every distant point becomes a message in transit, a fragment of a story that began long before our planet existed. And the deeper we look, the older the message becomes. The James Webb Space Telescope is able to read some of the oldest messages ever received, not because it travels through time, but because light does. Every photon Webb captures from the farthest galaxies began its journey when the universe itself was young. When those photons left their source, our sun had not formed, Earth did not exist. Even the Milky Way galaxy was still assembling many of the stars it contains today. For billions of years, those photons crossed expanding space. They passed through growing cosmic structures. They slipped between clusters of galaxies and through the filaments of the cosmic web. And eventually, after a journey almost as long as the age of the universe itself, a few of them arrived at a 6.5-meter mirror floating quietly 1.5 million kilometers from Earth. That moment, the instant when ancient light meets a modern telescope, is when cosmic history becomes observable. But what Webb reveals is not just the age of the universe, it reveals its transformation. Because when astronomers compare galaxies across different distances, they are effectively comparing different stages of the universe's life. Early galaxies appear compact, turbulent, intensely active. Gas is collapsing rapidly. Stars are forming in enormous clusters. Black holes are beginning to grow at the centers of young galaxies. These systems are still assembling themselves. They resemble cities under construction, structures rising quickly, streets still chaotic, energy everywhere. As time passes, galaxies grow larger. They merge with neighbors. Their gravitational motions settle. Disks begin to rotate more smoothly. Spiral arms appear. Elliptical galaxies form from earlier collisions. Star formation gradually slows as gas supplies diminish. The city becomes stable. The streets become organized. The explosive building phase gives way to long-term structure. Webb allows us to see both phases. In a single deep-field image, some galaxies belong to the early construction era, while others represent more mature systems. The sky becomes something like a layered memory, each layer holding a different age of the universe. And when you place those layers together, a remarkable truth becomes visible. The universe did not simply exist. It developed. Structure emerged from simplicity. The first stars formed from clouds of hydrogen. Those stars created heavier elements. Galaxies assembled from smaller pieces. Clusters formed along cosmic filaments. Over billions of years, complexity spread through the cosmos, and eventually that complexity reached a point where entirely new phenomena became possible. Planetary systems, organic chemistry, biology, conscious observers. When Webb studies the earliest galaxies, it is seeing the beginning of that chain of events. The early universe did not contain planets or life, but it contained the processes that would eventually make them possible. Stars forging elements, supernovae spreading them across space, gas clouds enriched with heavier atoms collapsing again to form new stars, each generation inheriting the legacy of the last. This gradual inheritance is one of the quiet engines of cosmic evolution. The universe remembers what its stars have done. Their elements remain in the gas from which new stars form. Their dust grains help cool collapsing clouds. Their explosions shape the structure of galaxies. And because Webb can observe galaxies from extremely early times, it allows astronomers to trace the beginnings of that inheritance. To see when oxygen first became common, to see when carbon began appearing in large quantities, to see when galaxies began containing the ingredients needed for planets. These discoveries do not just tell us about distant galaxies, they tell us about the origins of everything built from those elements, including ourselves. Every atom of oxygen in your lungs was forged in a star. Every atom of calcium in your bones was created in stellar fusion or explosive supernovae. Those atoms were scattered across space long before Earth formed. Over billions of years, they became part of interstellar clouds. Eventually, those clouds collapsed to form our Sun and the planets orbiting it. So when Webb observes distant galaxies forming stars billions of years ago, we are seeing earlier steps in a chain that eventually produced the material of our world. The connection is indirect, stretched across enormous spans of time. But it is real. Cosmic evolution is not separate from our story. It is the beginning of it. And this is perhaps the most extraordinary perspective Webb offers. For nearly 14 billion years, the universe has been changing. Gravity shaping matter, stars transforming chemistry, galaxies building structure, all of it unfolding long before any observer existed to notice. Now, in a quiet orbit far beyond the moon, a telescope gathers faint infrared light that began travelling before our species existed, light that left its source before our planet formed, light that carries the imprint of events billions of years in the past. And here, on a small world orbiting an ordinary star in a spiral galaxy, a species has become capable of receiving that light and understanding what it means. It is a strange and beautiful moment in cosmic history. The universe has reached a stage where part of itself can look backward across time and see how everything began to change, not through speculation alone, but through direct observation, through ancient photons arriving one by one. And as the James Webb Space Telescope continues its work, those photons keep arriving. Each one another piece of a story that stretches across the entire observable universe. A story of transformation, of stars igniting where there was once only darkness, of galaxies assembling themselves along invisible filaments, of matter gradually becoming more structured, more complex, more capable of forming new kinds of worlds. The deeper we look, the clearer that story becomes. And with every new observation, we are reminded of something quietly profound. The universe is not finished. It is still evolving, still building, still changing in ways that future observers, perhaps billions of years from now, will look back and try to understand, just as we are doing today. If you follow that chain of change far enough, you arrive at a strange and humbling realization. Everything we see in the night sky is part of an unfinished process. Galaxies are still forming stars. Black holes are still growing. Gas is still flowing along the vast filaments of the cosmic web. Even now, somewhere in the universe, new stars are igniting inside cold clouds of hydrogen that drift through distant galaxies. Around some of those stars, disks of dust and gas are slowly assembling planets. Entire solar systems are being born at this very moment. The universe is still in motion, but the scale of that motion is so immense that it often feels invisible to us. Human lives are brief. Civilizations rise and fall in the span of centuries. Even the entire history of our species occupies only a thin sliver of cosmic time. Compared to the age of the universe, humanity has existed for less than the final blink of an eye. And yet, Within that brief moment, something remarkable has happened. A species capable of asking questions about the universe has emerged. A species capable of building instruments that can capture light from galaxies billions of light years away. The James Webb Space Telescope is one of the most extraordinary expressions of that curiosity. Its golden mirrors unfold silently in the cold darkness beyond Earth's atmosphere. Its instruments detect faint infrared signals that began traveling toward us before our planet even existed. Every observation it makes is a small act of time travel, not by moving backward through time, but by receiving messages that have been in transit across the cosmos for billions of years. When Webb records the light of a distant galaxy, it is capturing a moment that happened long ago. A galaxy forming stars when the universe was young, gas clouds collapsing along the filaments of the cosmic web, black holes beginning to grow in the centers of newly assembled galaxies. Those events are ancient, yet the evidence of them arrives here and now. This is what makes the observable universe feel so extraordinary. We cannot watch a galaxy evolve across billions of years within a human lifetime. But because light travels at a finite speed, the sky contains many different ages of the universe simultaneously. Some galaxies show the universe as it is now. Others show the universe billions of years ago. The most distant ones reveal the earliest stages of cosmic structure. Together they form a living archive of cosmic history. And Webb is allowing us to read that archive more clearly than ever before. For centuries, astronomy often involved looking outward and wondering what distant objects might be like. Now we're beginning to measure them in detail. We can identify the elements inside galaxies that formed when the universe was still young. We can estimate how rapidly those galaxies were forming stars. We can trace how heavy elements spread across space as successive generations of stars lived and died. Each of these discoveries adds another layer to the story of cosmic evolution. Not a story told in a straight line, but one assembled from fragments of ancient light arriving from every direction in the sky. And the deeper we look, the more we realize how early the foundations of the modern universe were laid. The first stars ignited quickly. Galaxies assembled faster than many early models predicted. Chemical enrichment began sooner than expected. The young universe was not a quiet, empty place waiting patiently for complexity to appear. It was busy, active, full of energy and transformation. The cosmic web was gathering matter into filaments and clusters. Stars were forging the first heavy elements. Supernovae were scattering those elements into interstellar space. All of it happening hundreds of millions of years after the Big Bang. From those early beginnings, the universe gradually became more structured. Galaxies grew through mergers and star formation. Black holes expanded at their centers. Clusters of galaxies formed where cosmic filaments intersected. Over billions of years, these processes built the large-scale structure we see today. A universe filled with galaxies stretching across immense cosmic networks. Inside those galaxies, smaller stories unfolded. Stars formed planetary systems. Some planets developed atmospheres. In rare cases, chemistry may have become complex enough to support life. And eventually, on one small world orbiting an ordinary star in the Milky Way, a species emerged that could look up and ask where all of this came from. That species built telescopes, then bigger telescopes, then space telescopes, and finally, a telescope capable of detecting light from some of the earliest galaxies that ever existed. There is something quietly poetic about that moment. The atoms that make up the mirrors of the James Webb Space Telescope were forged inside ancient stars. The engineers and scientists who designed it are made of the same cosmic ingredients. And the photons it detects tonight began their journey billions of years ago, long before Earth formed. The universe created the materials for stars. Stars created the elements for planets. Planets eventually produced life. And life built a telescope that can look back across cosmic time to witness the early stages of the universe that made it possible. In that sense, Webb is not just observing cosmic evolution. It is part of it. Because the universe is not separate from the observers studying it. We are one of the outcomes of the same long chain of processes that Webb is now revealing in distant galaxies. Gravity shaping matter. Stars forging elements. Galaxies assembling across the cosmic web. The story written in ancient light eventually produced minds capable of reading it. And when you look at the night sky now, knowing that every distant galaxy belongs to a different moment in cosmic history, the universe begins to feel less like a static landscape and more like a vast unfolding narrative. A narrative that began nearly 14 billion years ago. A narrative written across billions of light years of expanding space. A narrative that continues even now, as new stars ignite and new galaxies slowly take shape. The James Webb Space Telescope has given us an extraordinary gift. It has allowed us to see that narrative more clearly, to recognize that the sky above us is not just a view into distance, but a view into time. A layered record of how the universe grew from its earliest galaxies into the vast cosmic web we inhabit today. And perhaps the most peaceful realization of all is this. The same universe that once seemed silent and unchanging is, in fact, alive with history. Every star, every galaxy, every faint glow in a deep web image is part of a story that has been unfolding for billions of years. A story that we are only now beginning to understand. And tonight, as ancient photons continue arriving from the farthest reaches of space, that story is still being written in light,